Hello, everybody, and welcome to another wonderful day of PChem. So today it's time for electronic selection rules part 2. This time for molecular systems instead of atomic. So similar to atomic systems, the place we're going to want to start with is a term symbol. But again, I do want to remind you that term symbols for molecular systems are a lot more loosey-goosey. Not everybody has every part of the term symbol. Everybody has an orbital angular momenta. Everybody has a multiplicity. Not everybody has Girard-Ungerad or plus or minus symmetry. And sometimes we just don't really care about the total angular momentum. However, that said, these symbols can help us to develop a set of fairly universal selection rules if you have the symmetry element of note. So the one we were going to want to start with is our good old friend orbital angular momentum. So in this case, the change of orbital angular momentum upon an electronic excitation should either be 0, +1, or -1. And this is going to be mostly useful as it's going to limit the change in the orbital angular momentum. So it is worth noting that we can, unlike previously, have no change in the orbital angular momenta of a system, unlike an atomic system. Now, one of the reasons why this is possible is our good old friend, rotational spectra. So if I have a rotational excitation, this is going to take up that angular momenta of the photon. So the electrons don't have to change their rotational speed. However, if they do, if they go ahead and increase or decrease in angular momenta, this will actually allow a system to generate no rotational change instead. So it can become rotationally silent because all of the angular momenta went straight into the electronic spectra instead. I told you it was coming at some point. However, the next major component is going to be our good old friend, the multiplicity or the spin. This is the same one as always. Spin can't change. So I should see no change in my spin, and this means also no change in my sigma, which is really the degree of orientation of the spin of the electron with respect to our angular momentum. Neither of these can change. These are called spin forbidden transitions. So only thing I can do is stay exactly where I'm at. This leaves us with our last of our classic atomic-like symbols of the total angular momenta change. And this is going to more or less obey the same rules as for our orbital angular momenta change, 0, +1, or -1, mostly depending upon how how my total orbital angular momenta change, because I'm not really seeing much change in the spin. So more or less, these are a much more freer version of our atomic orbital changes because now I've got a molecule. I can rotate. However, we now have generated a new set of constraints, and that's going to be our symmetry-based ones. So we're going to have a new set of rules based on symmetry. So we're going to go ahead and start off by looking at our planar symmetry. So it's worth noting that our planar selection rules are only going to occur for molecules with an orbital angular momentum of 0, because these are the only ones that do actually exhibit planar symmetry. Most of our molecules will tend to be symmetric, such as, say, N2 or C2, but we are going to have some molecules like O2 that are going to be anti-symmetric to a mirror. We're going to have some molecules like O2 that are going to be anti-symmetric to a mirror plane. However, when I'm going to be looking at these molecules with sigma orbital angular momenta, one of the things we should keep in mind is that the only type of angular momenta that will allow an excitation from a photon is going to be if the photon comes in along the z-axis. So essentially, it's coming along the bond. The other ones will be symmetry forbidden. However, it turns out that this photon coming in along the z-axis is going to have a positive planar symmetry because it's coming in along the plane, so it's going to be symmetric to any inversion. So now we're going to use our old friend, the trick of the transition dipole moment. So my transition dipole moment operator is going to have positive symmetry, which means that the only way for the total transition to be symmetric is if my initial and final wave functions share the same mirror plane symmetry. So if my initial wave function is symmetric, so does my final wave function. If my initial wave function is antisymmetric, my final wave function has to be antisymmetric. So for sigma orbital angular momenta, only possible transitions are plus to plus, minus to minus. No plus minus exchange, not allowed. So this actually helps simplify some of my allowed transitions. However, this also leaves us with one last type of symmetry we have to worry about. This is going to be inversion symmetry. So this is only going to occur for molecules that have a center of inversion. But if that does happen, first thing I'm going to need to do is, like I did with the last one, assign the symmetry of my incoming photon. So any incoming photon is going to have to be X, Y, or Z symmetric. And it turns out in inversion symmetry, as we've seen before, all of these are Ungerad. So if this guy's Ungerad, the only way for the net integral to be Gerard is if either my initial or final wave function is Ungerad and the other one is Gerard. So I can either have final wave function as symmetric, initial wave function as antisymmetric. This will allow me a real integral, or my final wave function can be antisymmetric and my initial wave function can be symmetric. Either way, really what we see is if I've got an inversion symmetry, we have what's called the Laporte selection rule. I can only have transitions of Ungerad to Gerard or Gerard to Ungerad. No Ungerad to Ungerad or Gerard to Gerard. More or less, my inversion symmetry has to change. And this is going to have some real implications for us later, studying quite a few real molecules. However, let's go ahead and try and focus in on some simple systems. Let's say I'm looking at O2. So as previously stated, we know that O2 has a ground state of a triplet sigma, antisymmetric to planar symmetry, symmetric to inversion. So we can identify three possible excited states by building up our MO diagrams and assigning symmetry, two of which are going to be triplet inversion antisymmetric, triplet sigma orbitals. One's antisymmetric to planar symmetry, one's symmetric. We also have one case where both electrons end up in the same orbital, which gives me a singlet delta and Gerard symmetric system. Now, let's figure out which one of these states is going to be allowable. So my first system, spin doesn't change, orbital angular momentum doesn't change, inversion symmetry does, but planar symmetry doesn't. Turns out all of those transitions are allowed. If I go to the next system, well, I'm allowed according to spin, angular momentum, and inversion, also known as parity, but planarity says no. So this transition is what's going to be called mildly forbidden. Most everything says it's okay. Planarity says no. More or less, it's going to be forbidden. Now, the last one is going to be forbidden by symmetry, orbital angular momentum, and parity. And planarity doesn't actually have anything to say because, well, it isn't sigma, so we don't have to worry. So we see that the first transition is going to be allowed. So we're going to expect to see a large signal here. The second signal is going to be mildly forbidden because only one of these four, and honestly, one of the less important ones, says no. The last one, we're not going to see any of because it's very forbidden. Momenta, spin, and parity all say heck no. And one of the important things to realize is that we're going to see selection rules not mean quite as much as they did for rotational or atomic or vibrational systems, because it turns out as I'm going to go from larger and larger molecules, and it's worth noting compared to what we see in O2 is fairly big, some of these selection constraints are going to become relaxed. And one way we can think about it, O2 vibrates. And with these vibrations, Well, I can slowly start deviating from parity and planarity. By the time we reach true molecular systems, this can play a real big role. So we're going to examine some of these molecular systems as we go forward. Till then, take care.